Welcome everyone. Good morning as well. Mark just told you about Quantum Application Lab and about the companies who are working together with Quantum Application Lab. We are one of those. And that's why I want to tell you a little bit about why we are doing this and also what we actually are. So we did a case on the with quantum computing for portfolio optimization, and specifically in the food and agriculture. So this is your slide, I see.
Yeah, just a short agenda. So first, Mischa will tell something about how, so what the scene is that we started with. Then I will go in short about what is portfolio optimization, how can quantum help there, and show some first results.
Yep. So we as a bank, we need to innovate. Banking is basically old-fashioned, but we need to change, and we need to change fast. Therefore, innovation should be part of our culture. And with Rabobank, I can tell you it is. It's part of our strategic agenda. And we are doing this not only for ourselves, but also to make the world better, because we want to make it possible for banking in the Netherlands and banking for food globally in a meaningful way. We are a large bank, especially on F&A and on commodity. On F&A, we are one of the largest banks in the world. And on commodities, we are one of the larger banks in Europe. We have done this for quite a long time, and we are still growing. We have a large market, as you can see. We're not only active in Europe, but also in the US, Australia, Asia, Africa, and South America. And in the Netherlands, we have over 9 million customers, and also a large market share in mortgages, insurance, and of course in lending. So why are we doing this? Food and agri, the business is changing a lot, not only because of new technology, but also because the society is changing, and we need to improve the world, and there's something big coming on, which is climate change. And therefore, we need to remodel the things we do. Normally, a bank looks at profit, revenue, and all kinds of margins on that side. But we also want to look at the food measurements, like nutrition and exposure. But also, we want to change things. So we have to look at and scale new KPIs, more focused on the Paris Agreement. So that's what we try to do within this model. And the details for that is going to be explained by Frank. So I think I can hand it over to you.
Okay. So I work for TNO, which is the Dutch research organization for applied science, and on a number of areas we work on quantum, and I'm in the group that works on quantum applications, and we took a look at this problem. So essentially, the problem that we looked at is about portfolio optimization. So what is portfolio optimization? The idea is that you have a number of assets or projects or whatever that you can invest in, and you want to have the optimal combination given the budget that you have, for example. And then you get a number of questions. So what is the best portfolio that you can generate? But also, what is best? So what are the indicators, the performance indicators that you want to value? Well, and in the classical portfolio optimization, mostly it's based on return and risk. So you want to have a high return, and you want to have a low risk, but but you cannot have them both at the same time. So you have to find a good mix of the two. So what you do then in most cases is that you can say, okay, well, I want to maximize my profit, but I want to have some bound on risk. So I want to have a maximum risk appetite, and I want to find that portfolio that gives the best profit for that risk. On the other hand, you can also think in the other way around. Then you can say, okay, I want to have some return. I define the return that I want, and I want the best portfolio that gives that return for the minimal risk. And then you will get probably different portfolios. Well, if you repeat that for all kind of different risk numbers or return numbers, then you actually get some line, which are all portfolios that in some way are good, because you can get a better portfolio in the sense that you cannot have more return against less risk. So each of the portfolios are best in some way. And all those portfolios together are on a line, and that is called the efficient frontier, or the Pareto, so it's the dilution frontier. And those portfolios are all of interest because they give you insight in how the trade-off is between both of the KPIs, so on both on return and on risk. So the two objectives we could also formulate in another way, so that you just say, okay, I have multiple objectives, and I want to weigh them in some way together, and then solve this problem. Well, and actually this is also the formulation that can be used in for example, quantum annealing, where a QBO, so a quadratic unconstrained binary optimization problem, has kind of this form. And then the objectives are mostly a linear or a quadratic form, which actually in portfolio optimization is in most cases, because risk is in most cases a quadratic objective. So what you can do then is take this optimization problem and then use the quantum annealer to sample from it. And what you hope to get there is that you get all kind of portfolios from that sampling from the quantum annealer, and that at the upper front, then you will get the best, so the Pareto or the efficient frontier that can then be used for the trade-off. So this is how we theoretically envision how we could do this on a quantum device. So if we again go to the Rabobank application, then so where we want to select assets, we actually want to select loans, or not select loans, but we want to define how much money is assigned to the loans that we have in our portfolio now in 10 years. So we actually want to create a growth path from the current situation to the situation within 10 years. And we are then interested in, okay, how will that portfolio act on both on return, so the return on capital, but also on risk, and in this case, it's the concentration risk. But that are not the only thing that are of interest. So as Mischa already said, we have a Paris-aligned decarbonization pathway that we want to include in this problem. So we put a cap on the emission intensity of the portfolio, and we add it as a constraint. That's the first constraint, and the other constraint is that each asset has a lower and an upper bound. Because we have a portfolio now, and we can act between certain bounds in the next year, so we can do a bit less or a bit more but there are some bounds on the height of each loan. So that we will take also into account. So what you can do then is draw something like this. And if you look at the problem, and you say, okay, well, for this case, we took 54 assets or companies that we could give a loan. And if we would also only be interested in selecting or the lower bound or the upper bound, then we already have 2 to the power 54 possible portfolios. But in real case, there are many more, because you can also take values in between the upper bound and the lower bound. And if you then would say, okay, well, I will just go and sample from this distribution, then you will get something like this. So these are all portfolios that are samples just from taking random values that are allowed within the upper and the lower bound. What we see here, the red dots and the green dots, that are actually the true Pareto fronts, where the red one is the unbounded one, so that doesn't take the emission bounds into consideration, and the green one is the one that we actually want to establish. So that is the Pareto front that also takes the emission into consideration. So what we see here is that if we sample from just the upper bound and the lower bounds, that well, it doesn't take the emission into account, so it will go all over, but it's not very close to the actual bound. And that's because, yeah, 80,000 portfolio out of 18, well, I don't know the number, but 18 times 10 to the 15th is quite small, and the good ones are not found by just sampling them. And also, and you might not see that, even if you're on the front row, that we have one, that's the orange dot here, portfolio out of the 18,000 that actually meets the emission criteria. So this is just random sampling. Okay, if we now build a QUBO for that, so the QUBO representation, and we use simulated annealing, then the picture goes this way. So actually, it's also kind of sampling, but it's two things. It's much more centered with results that are useful. So it's closer to what we actually want to achieve. And what you see is that you get much more. You had one, now you have thousands of portfolios that are actually meeting that emission bounds. But still, this is not quantum at all. So this is just a QUBO formulation, and then we use simulated annealing. But it gives some idea, okay, what would be possible by doing a QUBO formulation, because it's not a very straightforward way of modeling, because the actual ROC and the actual concentration risks are not a quadratic form in its own, so we have to do some manipulations to find a good QUBO formulation that estimates the real problem. Okay, but okay, we get somewhere, and then what we do is we run it on the real hardware. Okay, well, it's not as good as the simulated annealing one, but still, we see some form of where we want to get, and still we are able to generate portfolios that are really useful. And this is so based on the D-wave quantum annealer, and then just running the QPU, so no hybrid solutions or something like this. So what we see here, okay, well, this gives some hope that, by tuning it better or designing the QUBO with some, better suited formulas that we can come near to what we want to arrive. Okay, but then still what will be the gain? Well, of course, the gain that we want to have here is calculation time. Because what you see here is the calculation time that we have, and the scale is logarithmic. So the way that it's done now, so the dots that were calculated in what was it, orange and green, were generated by the classical method, and what we see here is based on the number of assets. Yeah, so the picture that we have here takes around 1,000 seconds to generate, but it will go quite quickly up to hours or even days in calculation time. And then you say, okay, but the simulated annealing one is also nice. It gives good results, but there also the calculation time goes up very rapidly. So that would not be a real alternative for bigger portfolios. And what we see on the real QPU, that the growth in calculation time is much slower. So we start quite high, and that's all about the embedding, finding the right embedding on the quantum device. But then we could only calculate it on the real device up to 100 assets, but there we say, okay, well, that slope is going quite slowly, and we expect that around 150 assets, then there the number of, so the calculation time will be lower already than the current simulated annealing. So that's where the expectant will be, so that in the coming years, when the number of qubits or the connectivity of the device will be better, then we will be able to come into this range of computations where we can do actually something that that would be quite nice. So some conclusions. So we think it is possible to approximate the efficient font share with a qubit formulation, and that can be done classically, but also using a QPU. And what we expect is that the QPU approach will be faster with bigger portfolios, but that we still have to tweak the formulation a bit to get better results. And both on those two items we are currently investigating to get this better. Yeah. So thank you for your attention. If you want to have more information, we are also at the booth of the Quantum Delta NL, and with the QR code you can find some information about the quantum team of TNO. And if there are any questions, we are happy to take them.
Great, thank you. One question? One question? Here?
Thank you for your presentation. Can you be please more specific about what's in your QUBO matrix? What did you put on either for what corresponds to each qubit? Like each qubit corresponds to what to do your optimization task?
So actually, the qubits are how did we model it? So what you saw is that we have an upper bound and a lower bound, and the way we encode is that we make a discrete steps between those, and for every variable we use a number of qubits that indicate on what place between the upper bound and the lower bound for each qubit are we. So this is how we encode the solution to or the problem to the QUBO, which is then put to the quantum annealer. And that means that actually the constraint of the upper and the lower bound is already the encoding itself.